we discussed how the commutation happens. The commutation always happens in the neutral plane, right? So where actually the current changes its direction when it is in the north pole in one direction and in south pole. As soon as it reaches the south pole, it starts reverting, or we can say it is commutating, right? So already we have seen this, and the process already we talked, we discussed how the current in fact commutates, and this plane is known as your neutral plane, okay? This is your neutral plane, where when the coil is placed in this plane, because it will not link with any flux, so therefore there will be no induced EMF in the coil, right? So whatever coil will be coming through this neutral plane, the induced EMF will be zero, okay? So therefore the brushes are placed always in the neutral plane, okay? Already we have seen this, and today we will see armature reaction. So these are the concepts which are common to both DC motor and DC generator. So what is armature reaction? The term reaction itself indicates that it has certain bad impact on induced EMF, or we can say efficiency of the machine, right? So what it means? So when the generator actually operating under no load, it is fine up to that point, because there will be no current in the armature winding, right? Only the EMF is induced in the armature coil till the point when the load is not connected. That means no load condition. I hope few of you have been done this open circuit test on DC generators. So when it is open circuit, it is fine. But when the load is connected, what will happen? As soon as the load is connected, the current starts flowing in the armature winding. When the current flows in the armature winding, what will happen? It will produce a flux, right? Because when the current is passing through a conductor, it will produce the magnetic field, right? So therefore, because armature coils are conductors, so when the current flows through this, it produces its own field. And that field, in fact, what it does, it distorts the main field. What the actual main field we have, it actually distorts it. So therefore we get reduced voltage. Okay? So how it happens, let us see. This is a picture where you can see, this is a cross-sectional view of a machine, where you can see north pole and south pole, and the machine is operating under no load condition, and the flux picture you are seeing here from north pole to south pole, and it is making paths through the magnetic circuit, right? Then it is making a closed circuit, right? Magnetic circuit. Now, if the load is connected, so before that, if the load is connected, what will happen? The armature will have some current, armature conductors. So now what will happen? These are the conductors. We are shown it in cross and dotted figure, right? So dot means the current is upward, and cross means current is downward to the surface, okay? Because it is a cross-sectional wave. Now we can see the flux lines produced by the current carrying conductors in the armature, okay? So now what will happen? This will have a impact on the main field, because main field is not shown here. So whatever flux is produced by the field, north and south, field poles, now it will be distorted, okay? Now we can see how it will be distorted, okay? So in one way, in one side the magnitude will increase, other side it will decrease, okay? So we'll see the waveform, pictorial view. Now this is the distortion, it will happen. Now because of this distortion, what will happen? The problem is the neutral plane shifts. Okay, where we fix the brush. Now, if we'll not change the brush position as per the loading of the machine, then what will happen? There is a huge spark, because the commutation should happen in the neutral plane only. If the commutation will force the commutation to happen in some other plane, then there will be a huge spark. Okay, so that will cause, in fact, distortion in the brushes, in the commutator segments will burn, right? So therefore, we need to shift the neutral plane as per the loading. As we vary the load, every time we need to change the neutral plane. Is it possible in practice? It is not possible. We cannot change every time we change the load. Every time we need to change the neutral, or need to change the brush axis. It is not possible. So therefore, there are certain mechanisms. We'll see how it will happen. How will counteract this armature reaction. Okay. Now we can see the north pole and south pole and the flux reduced by the north and south. This is the waveform of the flux, right? This is from the north pole, this is from the south pole. And the neutral plane is here. Okay, this is your neutral plane. Okay? Now, this is your armature, flux due to the armature conductors. So you can see here there are one solid line is there, one is dotted line. See, this dotted line shows the MMF, okay, and this solid line shows the flux. What is the relationship between flux and MMF? Phi equal to MMF upon reluctance. Okay. So therefore there is a difference in the shape we can see here. At the neutral plane, the flux is reduced, whereas MMF is same. Okay, MMF is increasing, again it is coming down in the south pole. But we can see the flux, it is actually have a shape of this, like a saddle point, right? So why this saddle point comes, the reduced value of the flux? It is because of the high reluctance in the neutral plane. Okay, so it is because of the high reluctance in the neutral plane, this saddle point comes, right? Saddle shape of the flux, it is coming into picture. Now, how it will affect, how this flux will affect the main flux. So this is how the main flux will be distorted. You can see it. It is very clearly mentioned, clearly shown. So this is your main flux. This is dotted line, right? Square shaped. This is the main flux. And now your flux by the armature is shown here in this plane, right? This is your flux from the armature. Okay? Now the distortion, how it happens, we can see here. This magnitude will reduce, because here we have a reduced magnitude, so it will reduce. Therefore, the net flux will have a reduced magnitude till this point. Then when it will increase from 0 to, it will become positive, then it will have increased value, right? So in some one part it will have a reduced magnitude, other part it will have a increased magnitude. Therefore the net flux will remain same, but there is a distortion in the wave shape. Therefore the neutral plane will shift. Now you can see previously the neutral plane is here. Okay, and now the neutral plane shifted to this point. You can see here. This is the shifted neutral plane. Okay, so this is the problem it causes. Because of the shifting of the neutral plane, there are many disadvantages in the machine. So we need to counteract this armature reaction so that your neutral plane should remain intact as before in the no load condition. So how we'll do this? Do you have any idea? How can I counteract? We cannot, in practice, we cannot shift the brushes every time we change the load.
अंदर मैग्नेट लगा सकते हैं
कहाँ पे?
रोटर के अंदर
रोटर के अंदर?
अपोज करेगा
रोटर के अंदर लगाएंगे तो कैसे अपोज करें? रोटर इज रोटेटिंग. We should fix it in the starter. You are correct, but we have to fix it in the starter. So now the question is, where we need to fix that poles or those magnets in the starter? In the neutral plane itself. Okay. So those are known as the interpoles or compensating poles. Okay. Sometimes we call it interpoles because it is placed in between the main poles, or sometimes we call it compensating poles. Okay. Now we can see what are the countermeasures we can take. So some of the measures that are being used to combat armature reaction is that first point I have discussed this, that first we can change the brass position every time we change the load, which is actually not practically feasible. So therefore what we need to do, interpoles or commutating poles, as they are sometimes called as narrow poles, they are smaller in size, that may be located in the interpolar region, centered along the mechanical neutral axis of the generator. So it will be centered around the neutral plane or neutral axis, right? And they are smaller in size. They can be placed in between the main poles. Okay. So this is how we can place the interpoles. You can see here, this is one pole, this is one pole, this is north and south, right? Now whatever flux will be produced by the armature, because the flux will pass through this, right? North through south. Now the windings of the north and south pole, the interpoles, will be connected in series with the armature. As soon as we connected the load, the same current will flow through the interpole as well as the armature, right? Same magnitude, therefore it will be easy to counteract the same amount of flux produced by the armature, right? So now armature produces in this direction, now this will produce in this direction, so it will counteract the flux produced by the armature. Now we need to change the brass position because the neutral plane will remain as it is, right? Now another method is there to nullify the effect of armature reaction, that is called compensating winding mechanism. So what is this compensating winding mechanism? We create the slot across the pole surface, okay? And in the pole surface itself, we will put the rings, the bar structure, or we can say the windings, right, in the slots, like we can see here, right? So here, this is your main pole, right, north pole and south pole, okay? And these are the field windings we are seeing here, right, main field winding. Now there are slots we created in the pole surface itself where we can put the windings which will be connected in series with the armature, and that will also have the counteracting effect on the armature flux. Okay, so this is how there are two major methods we have. Sometimes if it is very large machine, then both are used, interpoles and compensating windings. Okay, if it is a small machine, then only interpoles or compensating windings can counteract the armature reaction. Okay, so I hope everybody understood this concept, right? Okay, any doubt till this point? No doubt. Now this is the interpole structure, right? Okay, so this concept is over, which is actually we are talking for both motors and generators. Now I'll talk about different types of DC generators. So already I talked in the first class, very beginning, what are the types of DC generators, right? So major classification if we do, one is your separately excited DC generator, and other classification is self-excited DC generator, right? Okay. Now, in the separately excited, now the question is, in which category the permanent magnet generator will come into? Huh? In which category this permanent magnet generator will come? Huh? Huh? Everybody is wrong. It will be separately excited, right? Because we are not exciting what generator is producing. It is a permanent magnet, so we can say it permanent magnet separately excited DC generator. So it will come into the category of separately excited DC generator. In other way, the separately excited generators also can be excited by some external source. Like we are having in the machine lab also, we have a external DC source, that is a rectifier circuit, and through the rectifier circuit we can excite the field of the generator. Okay, so that is external. From the external source also we can excite so that is also known as separately excited DC generator. Okay, now coming to the separately self-excited DC generator, already I told you they may be shunt connected, okay, and series connected. It is based on the structure and connection of the field winding. May be compound connected, okay. So what is shunt connected? In shunt connected generator, the field winding is connected in shunt in parallel with the armature winding, right? Across the armature winding. And in case of series connected, the field winding is connected in series with the armature winding, right? And compound connected, both series and shunt windings are there, but they are also again classified into cumulatively and differentially. Okay. So cumulatively means when your series field is aiding the shunt field, then cumulatively compound generator, and when the series field is actually not aiding, it is not supporting the main field or the shunt field, then it is differential compound. Okay, so this is the major classification. Now we'll read individually each of the generators characteristic separately. Okay. Now what characteristic we'll study? Because first characteristic what we talked about is OCC, that already common for all, no need to discuss. Now what is the characteristic which will be different for individual generators? That is the external characteristic. Okay, so what is that external characteristic and why it is essentially required to study? External characteristic is the characteristic which is actually plotted using the terminal quantities. So for both generator and motor, the terminal quantities are different, right? So what are the terminal quantities of the motor and what are the terminal quantities of the generator? What are the terminal quantities of the motor?
Low voltage and maximum current.
That is for generator. For generator, the voltage across the load, or we can say terminal voltage, and the load current. These are the terminal quantities of the generator. And the terminal quantities of the motor. What are the terminal quantities of the motor?
How much it can be power
Yes.
and the maximum current it can.
Terminal quantities of the motor is, we basically generally when we use the motor, we basically measure the torque, how much torque it produces, how much torque is required to drive a load, right? So that is the measurement, right? So therefore torque is one of the parameter, terminal parameter, and other one is speed. Speed of the motor, because speed is essentially required for any drive system. Any system we use or apply the motor, the speed plays very important role, right? Okay, like a fan, we need speed, right? Speed and torque, both measurement is required. So motor terminal quantities are speed and torque, and the generator terminal quantities are voltage and current, right? Now we'll see the characteristic of these generators, external characteristic of the generators between the terminal voltage and the load current, right? Okay. So before we move forward, what is voltage regulation? Let us talk about voltage regulation. Already I have shown the equation. Voltage regulation is V no load minus V full load divided by V full load into 100. Already you have been taught in your transformer course as well, right? So why voltage regulation is essentially required? This is a parameter by which we can actually measure the effectiveness of a machine, okay? Because it is generator. It may not be required for the motor, but being a generator, it is required to know how much voltage regulation the generator is providing. Because the terminal voltages plays very important role to drive the load, electrical loads, right? So therefore voltage regulation is V no load and minus V full load by V full. So what is V no load? That is when the load is not connected, that is open circuit. Under that condition you measure across the terminal of the generator when you connect the voltmeter. Then whatever reading the voltmeter will show, that is the no load voltage, or we can say voltage under no load, right? Then full load voltage means when you connect the full load means the rated load to the generator. Suppose your load generator is rated at 3 kilowatt. So if I connect the 3 kilowatt load, have you seen the load works in our machine lab? Yes. So you will connect the 3 kilowatt load across the generator. What is then will measure the voltage across the terminal. What voltage it will show? It is the full load voltage. Okay. So through the measurement we can find it easily, right? Okay. Now next, moving to the power flow diagram. Power flow in a DC generator specifically. So how the power flows in case of DC generator? So input power, what we give to the DC generator, what is it? It is the mechanical power, right? And this mechanical power is this P input. How we can measure it? We can just multiplying the torque, supplied torque into the speed of the machine, right? Or speed of the drive. We can say that if the generator is driven by a motor or driven by engine, or let us say diesel engine, right? So what is the speed of the shaft of the diesel engine and the torque provided by the diesel engine? It will give me the input power, okay? Now as soon as we give this input power to the generator has certain losses, right? So always we know that P input is equal to P out plus P losses. P losses means what are the losses incurred inside the generator, right? So what are the losses incurred in the generator? So before moving, there are first, when we give the mechanical torque to the generator, right? So it will produce some losses in terms of mechanical quantities, right? We call it mechanical loss. Because it is rotating, it is supported on a bearing, right? When it rotates, it has a frictional loss, right? On the bearing itself. So that frictional loss is, what are the other mechanical losses? Can anybody tell? One is a frictional loss. Other is Mechanical laws. Huh? Any other laws we consider under mechanical laws? Any other loss happens inside the generator which can be contributing to the mechanical loss. Huh? It may be due to mechanical, but it is because of the friction only, right? It is because of the friction. And other heat is produced because of the copper loss. Right? That is electrical loss.
Because of fault, maybe alignment, use it or
That is when we are not considering a fault in the machine, right? So when the fault is there, there will be different kinds of phenomena happen, right? What are the other losses, mechanical losses? One is the friction loss. Then, so there will be resistance to the wind, right, inside the machine. Huh? Because air is the fluid inside the machine, right? And when the machine will rotate, there is a opposing resistance of the wind, right? And that, because of that also, some loss takes place. That is known as windage loss.
Which kind of friction?
It is a friction, but it is not actually friction, but it is a loss in the fluid, right, in the medium itself. So therefore, so these two kinds of losses then will happen, right? Now, after the friction loss, after this we can categorize into as rotational loss. This is rotational loss, right? So this, after this rotational loss, whatever power will get, now here P in minus PR, whatever power will get, let us say it is PD. Okay? So now PD is equal to whatever, it is the developed power, right? Now this power will be utilized, right? In case in the generator. Now this PD will be equal to internal EMF generated or induced EMF in the generator into IA. Okay, whatever is mentioned here, right? And that is equal to TD omega M. Already we discussed this, right? TD omega M. This is a developed power, okay, inside the generator, right? And now we have another loss because of the electrical circuit inside the generator. That is known as copper loss. Okay, and copper loss takes place everywhere where there is a winding. There is a conductor, copper loss takes place. Like in the field also it happens, in armature it also happens. Right? Okay. Apart from this, there is another loss. We call it magnetic loss. We are actually forgetting this. This is an important loss, right? So what is this magnetic loss?
leakage in flux.
It is because of the leakage of the flux maybe, but mainly magnetic flux includes hysteresis loss and eddy current loss. Okay. So both will be there. So therefore, this magnetic loss is incorporated in this rotational loss as well, because after the magnetic loss only we will have this developed power, PD. Okay. So that means I can write here PR is equal to P mechanical plus P magnetic. Okay. So that will give me the PR. Now PD is P in minus PR and PD minus PCU is your P out. Okay. So what is this copper loss? Copper loss is in the armature circuit, right, as well as in the field circuit. Okay. And P out also I can write in terms of voltage and current, that is terminal voltage into the load current. Okay. So up to this part everybody is clear? Okay. Now we'll consider a separately excited generator and we'll discuss the governing equations and also we'll discuss about the where you are going and we'll discuss the external characteristics. Okay? So now because I talked in the first class, we'll only talk about the steady state analysis. We are not going to discuss here the dynamics of the system, dynamics of the generator, because it is advanced level course, right? Because if we are going to consider dynamics, there are many phenomena we need to consider, like the inertia of the machine, like the inductances, everything we need to consider. So we are only going to consider under steady state analysis. Therefore, this can be represented through only the armature resistance Ra, okay, and the field resistance Rfw. So in the field winding there will be, of course there are inductances, but because we are not considering the dynamic phenomenon, so here therefore under steady state the inductances can be neglected and therefore we are considering only the resistive parameters. In the field circuit we are considering Rfw, that is the resistance of the field winding, and Ra is the resistance of the armature circuit, armature winding, right? Now because this is a separately excited generator, so therefore the field is excited through one external source, that is Vf, okay, and this Nf represents the number of turns in the field winding, okay. And here in the field circuit we are seeing another variable resistance is there, that is Rfx. Why it is essentially required? Those who have performed the experiment, they might be knowing what is this, why this variable resistance is required in the field circuit. Regulate the voltage by regulating the current in the field circuit, okay. So when you regulate the current in the field circuit, the phi will change, right? As the phi will change, the voltage will also change. So therefore, this field variable resistance is required to control the current in the field winding, that is If, okay. Okay. So now, now we'll see the governing equation for this. So what will be the in this circuit particularly, what will be the equation for Vt? The current, let us say, current is already marked Ia, right? So now can you write the equation for Vt? This is very simple resistive circuit. Now you can write it as Ea minus Ia. Very simple, right? And this is in fact the governing equation for the armature circuit for a separately excited generator, right? Vt equal to Ea, or in other way you can write Ea equal to Vt plus Ia, right? And what is Ea? We already derived expression for Ea, that is K phi p omega m, right? Okay. And Vt is the terminal voltage, and we know this Vt, it will across the load, right? Now if we write the equation for the field circuit, so it will be Vf will be equal to If into Rfw plus Rfx. These are very simple equations, right? And now can we plot the external characteristic using this equation? This is a terminal voltage and induced EMF and armature current, right? Can we plot now? I hope you can plot it, right? Can you plot? This is a very simple equation. You have to plot it. Voltage, load voltage and load current, that's all. Load voltage is Vt and load current is Ia.
So y equal to mx plus c.
Very good. Right? Y equal to mx plus c. So it will have a negative slope, right? This can you draw it? So I hope everybody can do it. So no need to discuss further. And here I will show you the characteristic. Right? So now the dotted line you are seeing here. So this is the plot between Vt and Ia. Ia, okay? Okay. So now, again and again it is going to the problem page because everybody's, the problem is, I think you are very interested to do, so that's okay. So Vt and Ia. So now if we'll see this dotted line, this is under no load condition. So VNL will be equal to EA, that is induced EMF, right? Okay. And now if we'll plot this Vt equal to EA minus IARA, so this will be this dotted line, right? Okay. Correct? It is correct, right? Now, why this curved line is coming into picture? This obviously this is a drop, armature resistance drop, this gap, right? And as the load current will increase, it will also increase, right? But why this curved line is coming? It is because of the armature reaction, okay? When the armature reaction is present, it is not counteracted properly, then your characteristic will become non-linear. It will not remain linear as we are seeing here. Vt equal to EA minus IARA. Okay, it will change. Why it will change? Why it will change? Why it will become non-linear? EA, we know EA is a function of. I can write it A. I can write it EA is function of phi, right? Phi p. Now because of the armature reaction, this phi p will change, right? And this phi p is not changing linearly, right? So it may change based upon we have seen the nonlinearity behind how it will counteract, right? The armature reaction. Therefore, this terminal voltage will become a curve, right? Okay. And that is because of the armature reaction drop as shown here, right? So I hope you understood this characteristic, external characteristic. And this is in fact very essentially required. We need to know before the application of a generator to a particular load. Okay? Because if the load characteristic and the generator characteristic, there is a mismatch, we cannot use the generator for that particular application. Okay? Okay, here is a problem.